Good morning, everyone. So today, in this session, we will be talking about the density functional theory, the introduction to it, and the basics of DFT. So, the content will be like we will see a brief picture how we transition from classical to quantum era, and in perspective to the density functional theory, and we'll talk about the basic formulation of Schrodinger equation, and then Hartree and Hartree-Fock method. And then we will also see a brief of Thomas Fermi theory, and then our famous Weinberg-Kohn theorems and exchange correlations, and then we will see how we can solve these Kohn-Sham equations in density functional theory and the approach to do it. So Hamilton, he gave the famous Hamiltonian for any system. So that is nothing but the Hamiltonian is the total energy, that is the kinetic energy plus the potential energy. So it was given long back around 1833. So at that time, people were doing experiments, and mostly they were doing in early 19th century. They used to do study of spectra, atomic spectra, and molecular spectra. So there were a lot of data for atomic spectra, especially like hydrogen and helium and iron and many metals. So at that time, there was like problem that there was no theory available which could prove or which could explain the spectra of any atom or any molecule. So both try to give a model, which is very simple model, that the energy difference between the excited state and the ground state will give you the emit the radiation of frequency f, and h is a Planck's constant. So the model of Bohr's was good for hydrogen, but beyond hydrogen, like helium and other multi-electron elements, it was not able to predict the spectrum with this Bohr theory. So there were drawbacks for this Bohr theory, or we can say the limitation that it cannot be applied to multi-electron atoms or systems. And also this Bohr theory was a classical picture, or we say rather semi-classical picture, and it does not contain the quantum phenomena which used to happen, which happens in atoms. And also it cannot explain the spectral line splitting in any of the spectra. So people were trying hard to give a model or theory which can explain the spectra or which can explain the atomic structure of system. So when in 1926, when Schrodinger first gave his Schrodinger equation, so this is nothing but a kind of an Hamiltonian for many body system, where we have a wave function psi, which is nothing which is composed of the coordinates of all the electrons in a system. Suppose if there are n electrons and m number of nuclei, and we have the coordinates of all the nuclei, and h is the Hamiltonian of the many body system. So when we apply this h on psi, we will get the energy of the system, and we will have the wave function. So this Schrodinger Hamiltonian equation contains 5 different terms which are given as below. So the first term in the Schrodinger equation is the kinetic energy of electrons. Since electrons are moving in a material, so it will have a kinetic energy. And then we will have the kinetic energy of nuclei, all the nuclei. And then we will have the electron interacting with the nucleus, so that will also contribute an energy term, that is electron nucleus interaction energy term. And then we will have the electron interaction, because the electron will interact with other electrons in the system since it's moving, so they will have an energy contribution to the Hamiltonian. And then finally we have the nucleus interaction energy, because these electrons and nucleus are charged bodies, so they will interact via Coulomb interaction, and since they are moving in the system, so they will also have a kinetic energy. So this is a complete Hamiltonian of many body Schrodinger many body system. And out of these, we will see that Bohm and Oppenheimer, they gave an approximation that is known as adiabatic approximation. And it simply says that when the nucleus, if the nucleus is moving in the system, then that will not exchange energy with the external system or outer environment. And in simple terms, it is explained as the nucleus, since it is much heavier than the electrons, like 2000 times heavier than the electrons. So that nucleus movement is neglected, or it is considered negligible in comparison to the movement of electrons, and the kinetic energy contributed by the nucleus is almost zero. So we will neglect this term. This term is neglected. And also in the system, the nucleus are since fixed at a particular sites, lattice sites, so they are not going to move. So the kinetic, the interaction energy between the nuclei among themselves is going to be a constant for a particular kind of system. So this term we will forget for time being, and it is a constant. So we can solve this Hamiltonian for only three terms, that is kinetic energy of electrons, electron nucleus interaction energy, and electron interaction energy. And then further we will add this external potential or nucleus interaction energy to the final our total energy. And what we have to solve is we have to solve only the electronic part of the Schrodinger equation, that is kinetic energy of electrons, electron nucleus interaction energy, and electron interaction energy. So our total energy will be composed of two parts, that is an energy coming from the electron interactions and the energy coming from the nucleus interaction. So the first attempt made by Hartree was to solve this equation, and he did consider that he tried to take a multi-electron system, and he considered one electron at a time and tried to solve the Schrodinger equation by a self-consistent method. We will talk about self-consistent method in brief, how it is done. So in Hartree method, we have this kinetic energy of electron and electron nucleus interaction energy and electron interaction energy. So for n number of electrons, we will have n number of equations, because we are solving taking one electron at a time and solving for all n electrons n number of times. And also the wave function for this n electron system will be composed of n number of wave functions for each atoms. So this method says it takes one electron at a time. It was simpler to solve for hydrogen atom because the hydrogen has only one electron. And from this model, from this Hartree theory, the ground state or the energy for the hydrogen atom comes out to be minus 13.6 electron volt. And it is also confirmed from the experiment that the ground state energy, the total energy for the hydrogen atom is minus 13.6. So this Hartree method was very good to solve one electron system, but it fails for multi-electron system, because there are a few reasons we will talk about as we progress. So this was given in 1928, but before that, Pauli's exclusion principle was proposed by Pauli in 1925, and after that, the next year, the electron spin was confirmed. So when electron spin was confirmed experimentally, so Pauli's exclusion principle was now valid for electronic systems. And in 1926, Heisenberg and Dirac, they proposed that since the electrons have a spin and they, due to exclusion principle, the two electrons cannot be at the same site. So the wave function for the electrons should be antisymmetric so that it can follow the Pauli's exclusion principle. So applying all these things like spin of electron, the antisymmetric properties of the wave function of electrons, so Fock did a modification in the Hartree method in 1930, and he came up that if we exchange the position of two electrons, say, so this R1 is, sorry. So if R1 and R2 are exchanged, so we'll get a negative antisymmetric wave function. So with this application in Hartree method, so what we had is, we have the kinetic energy of electrons, and we have electron nucleus energy, and we have electron interaction energy. And applying this antisymmetric properties into the Hartree method, we get the Hartree-Fock method, and we had one extra term in the energy, that is, we had kinetic energy, electron nucleus interaction energy, and we had that is Hartree energy, that is electron interaction energy, and we have one energy term extra, that is exchange energy, EX. And that comes from the antisymmetric nature of the electronic wave function. So to solve those Schrodinger equation, so we generally use two methods, that is variational method and self-consistent method. So when a system doesn't have a state which accommodates more than one or two energies, like in a state, if there are more than one energy states, so that is system is degenerate. And if the system is non-degenerate, then that means we will only have a one particular state. That is will be the ground state if you solve this Schrodinger equation. And if in this Schrodinger, in this Hartree-Fock equation or the Schrodinger equation, if you say in general, if you solve for this wave function, if you minimize this Schrodinger equation with respect to the wave function, so we'll get a ground state energy. And this is the variation principle where we minimize our Hamiltonian with respect to psi and we get the minimum. So in Hartree-Fock methods, the assumptions were that the system of n electrons that will have n wave functions. So we have to consider n number of wave functions for all those n electrons. And we have to calculate all those three terms, that is kinetic energy of electrons and the electron nucleus interaction energy and electron-electron interaction energy. And then that equation, the Hartree-Fock equation or Schrodinger equation, we put our psi and we will solve that and we get each energy values corresponding to each electrons or each size. And we do for n number of electrons, and we repeat this process of solving the wave equation for taking psi and getting the energy and then putting the energy in the system and then again getting psi self-consistently till we get a minimum of the energy, and that then we say that this Schrodinger equation is solved and we get the ground state energy. So this process we will discuss later on. So these Hartree and Hartree-Fock methods were based on wave function approach. So the first attempt to use the electron density as a variable in solving the Schrodinger equation was given by Thomas and Fermi around 1928. And what they considered is they considered the kinetic energy of the electron as non-interacting. They assume that the electrons are not interacting with each other. So this first term is the kinetic energy of non-interacting electrons. And then there is second term, which is the electron nucleus interaction energy. And also the third term is the electron-electron interaction energy, the same as the Hartree terms. But here these energy terms are represented in forms of electron density Nr. And since we, in this Thomas Fermi model also, we solve this energy functional with respect to the density. We minimize the energy functional with respect to the density, having a constraint that the number of electrons in the system should not change, or it should be conserved. And when we do this, we use a method of using Lagrange multiplier, constant mu, and we minimize the total energy E, Thomas Fermi, with respect to total number of number of electrons conserved in the system, and we get the final Thomas Fermi equation as in this form. So, and from there we solve for n, we get the density, and then we put into the Thomas Fermi functional here, and we solve for our total energy ETF, Thomas Fermi energy. So there were major drawbacks in this Thomas Fermi model is, since the number of electrons in the system is taken as constant or it is conserved, that means each atom in the system has a fixed number of electrons and no electrons are given or taken by any other atoms. That means the sharing of electrons is not prohibited. So it does not predict the bonding nature of any solid or molecule. So according to this theory, the molecule, the solid cannot form. So it is only valid for isolated atoms. And also the kinetic energy, that this first term, 5 by 3 AKN R to the power 2 by 3. So this kinetic energy term is very much approximated in a crude manner. How? Because this kinetic energy is assumed that the electrons are free in the material, they are not interacting, so it will occupy a level up to the Fermi wave vector, and then we will have all the states filled up to the Fermi wave vector, and we can total sum of the energies of all the states filled up to Fermi wave vector kf, and we will get a total kinetic energy and integrating over all k spaces. So this is a very crude observation because there is no there is no quantum interaction involved. So the kinetic energy is wrongly estimated, and it gives a wrong ground state or wrong property of the system. And also the electron-electron interaction is classically treated in this model. So the quantum phenomena are totally omitted, and we do not get any exchange interaction as it was given in Hartree-Fock method. So the attempts were made to use electron density or electronic charge density to calculate the property of the matter, any material or any many-body system, but that failed. So people tried. So this was in around 1928, and after many years, around 1964, the famous density functional theory was developed by Hornberg, Kohn, and Sham. So before that, we will talk what is electron density. So electron density is nothing but the number of electrons per unit volume. The way we calculate density for anything, that is similar for the electron density also. So for any system which has n number of electrons and it has a volume V, so the electron density will be simply n by V. So here you see this is an example for silicon atom. So silicon has core electron as 1s, 2s, 2p, and the valence electron are 3s and 3p. So core electrons are near to the nucleus, and the valence electrons are far away from the nucleus at around 2 atomic unit of distance. So here this is the charge density of the silicon atom in its unit cell. So you can see the red colors marked on the right hand side in this picture are the electronic charge densities, and you can see the charge density is also present away from the atoms. So atoms are in blue color, silicon atoms, and we can see the red charge density, the electronic charge density is distributed all along the bonds and away from the atom nucleus. So the valence electrons are spreaded in the system, and that also contributes to the electron density, mainly for our computational purpose. We will talk later on. So the electron density is simple. This total number of electrons divided by unit volume. So around 1964, around say 40 years, after 40 years of Thomas Fermi and Hartree-Fock method, Hornberg and Kohn, they gave two theorems, and they prove for that. They give the proof for that theorem in their two papers. And Kohn was awarded Nobel Prize for that method. So first theorem is the electron density will be the main variable in solving the many-body Schrodinger equation. And it states that since in any system, the nucleus positions are fixed, so that that nucleus-nucleus interaction energy is constant. And the way each electron and each nucleus interacts, that depends only on the system, because in each material, how separated are the electrons and nuclei, that is particular to that particular system. So if you take example of hydrogen and helium, the one electron of helium, that radius between the nucleus and electron will be different from the electron that is radius from the nucleus and electron in helium, and so in iron or other atoms. So that external potential is unique to a particular system. And if we measure this external potential or electron nucleus interaction energy, so then we can apply it to that system and we can solve. And also the ground state energy of any system will be achieved by minimizing our density with respect to minimizing our Schrodinger equation or many-body Schrodinger equation with respect to the density, and at a point where we get the minimum of the energy and we cannot no longer reduce the energy of the system, at that point we will get the minimum energy, and that density corresponding to that energy will be our ground state density. So there are two things that we have to find the potential, that is electron nucleus interaction energy, and we have to find the ground state density of the system. So if you solve that, if you remember the picture, previous energy terms, that is the total energy of the system will be composed of the kinetic energy of electrons, and we will have electron nucleus interaction energy, that is E external, and we have electron-electron interaction energy, that is E Hartree, EH, and we will have E exchange because of antisymmetric nature of the wave function. So in order to solve the Heisenberg-Kohn theorem, so there was an assumption that the n electron system will be decomposed into one electron system, but n number of times. So n electron system will be decomposed into n number of one electron system. So we will solve only one electron system, but n number of times instead of solving n electron system. And then we will have this n electron systems where the electrons are interacting with each other as one electron system, but the electron is not interacting. So the ideal picture is we have n electron system and the electrons are interacting. We will assume as non-interacting one electron system, but n number of systems. So in this assumption of Heisenberg-Kohn's theorem, what they did is they decompose the kinetic energy of electron into two terms. That is the kinetic energy of non-interacting electrons as well as the kinetic energy of interacting electrons. So now we have break this kinetic energy part. And then also in exchange and Hartree term, since the electrons are interacting with each other, EH, so this term will be as it is, and there is an exchange term because of antisymmetric nature of electrons, this term, and since the electrons is interacting, so we will add an additional term, that is E interacting term. Okay. So our total energy will be now, if you see this equation, will be E Hartree, E exchange, and there, since the electrons are interacting, so we will have Hartree exchange and an additional term of interacting term, and later we will name that term also. So we can make this Hartree and exchange term as well as C interaction term as exchange term plus correlation term. So what we have done is we have broken the kinetic energy into different parts, non-interacting and interacting. Someone wants to say something?
Hi, I think
Yes.
there is some problem with someone, and if I am muting, then it's getting unmuted. So, hi. Let me do one thing. Yeah, I am muted. I can go ahead.
Okay. So the basic idea of this assumption of Heisenberg and Kohn is we will break our kinetic energy terms into two terms, non-interacting, so that it's easier to solve. And we have an interacting term of kinetic energy. We have the Hartree term, we have the exchange term. So all those interacting terms will now be clubbed together as EC, correlation term, and we will have the exchange term as it is. So our total energy will now be given as kinetic energy of non-interacting electrons, electron nucleus interaction energy, that is external energy, which is unique to a system, and we will have the Hartree energy, that is electron-electron interaction energy, and all those interacting terms in the kinetic energy, all also in the electron-electron interaction energy will be clubbed as exchange correlation energy, that is EXC. And this total energy will now be, which depends on the density.
Hello, sir, if you don't mind, I have a doubt, sir. Shall I ask now?
Yeah, sure.
This external energy, why this nucleus electron interaction energy is called as external energy, sir?
Why is it called as external energy?
It should be internal only, no? So why?
No. So external It's not because of it is inside system or outside the system. It is called as external energy from the point of view that it is it is not a part of the interaction energy of electrons or the correlation effect or the quantum effect. So see, we have a system where there are classical Coulomb interaction happening between electron and nucleus. Okay. And also we have a classical interaction happening between electron. And also there is a kind of quantum interaction happening between electron and electron. And that is not happening between electron and nucleus. Okay. So this interaction of electron and nucleus is purely classical, it's Coulomb in nature. So this is external from the point of view that it is different from the quantum interaction of electrons in the system.
Okay, okay, sir. Thank you, sir. Thank you, sir.
And all those terms, see, if you see the final expression is that we will have a function of density and we will have external potential. So this F rho r or this non-interacting term and EH and EXE term, we have to solve with approximation. And this term EXT will be constant in a system. If you solve it for once for a system, suppose for hydrogen or for helium or for iron, so you're not going to change whether you take one iron atom or two iron atom. Okay, because the distance between nucleus and electrons are going to be fixed in that particular atom, because the orbitals are fixed in an atom. So that interaction is constant, and you can use either you are taking iron in pure iron compound, or if you are taking iron in Fe2O3 or any material. Okay, so that is external from that point of view. So our total energy will be functional of density as well as one term of E external, that is electron nucleus interaction energy. And this functional of density has terms non-kinetic energy, because the electrons are moving. So how the electrons are moving or in which pattern the electron is distributed, that will decide the density of the electron in the system. So this non-interacting kinetic part of the energy will depend on how the electron density is distributed in the system, how the electron density is. So it is a dense part, or it can be calculated from the electron density. And also the interaction between electron and electron, that is E Hartree, that is also depend upon how the electrons are distributed in the system. So if the electrons are situated too apart, very far apart, so the density will be different within that two electrons, or they are very near, so the density will be very high in the system. So these electron interaction energy, that is EH term, will also depend on how the electron is distributed in the system. And also the exchange correlation, that is the antisymmetric nature of the electron, and also one quantum exchange term that we'll talk about later. That will also depend how the electron are situated in the atom, in the system, or in our many body system. So these three terms will depend on the electronic density, and the external term is independent of the electron density, and it is also called as external term. So if you see from picture representation, that on the left hand side, we have all those four terms: the kinetic energy of electron before the assumption of Hartree and Kohn and Sham. Okay, and we have the external potential, we have the Hartree energy, and we have the exchange energy. So this picture is represented in Hartree-Fock method. So the Hornberg-Kohn theorem assumption was they decomposed this kinetic energy term into kinetic energy of non-interacting electrons and kinetic energy of interacting electrons. The external potential, external energy is constant. There is not going to change. It is similar in Hartree-Fock method as well as in Hornberg-Kohn methods. And the Hartree energy is also same. And this exchange energy, the energy between the energy due to the exchange of electrons, which exchange the position of electrons, also coming from the antisymmetric nature of the electronic wave function. This is also decomposed into two parts, that is exchange energy and correlation energy. And then we club all those interaction energy into each term, and we get our final energy forms in Hornberg-Kohn theorem as kinetic energy of non-interacting electrons, external energy, Hartree energy, and another term is exchange correlation energy. So this exchange correlation energy is different from the Hartree term, and that is what makes this Hornbook-Kamm approach different from the Hartree fog, and that is why it is more accurate in terms of the energy. So also we can understand this Hornbook-Kamm theorem approaches is see on the left hand side, we have n number of electronic systems. So each electrons are interacting with each other. Yes.
Hello, sir. Sorry,
Yes.
sir.
Yes.
Sir, in the previous slide,
Yes.
yeah, you have this exchange energy in Hartree fog system is actually divided into two parts. One is exchange energy, the other one is correlation energy, sir.
Yes. Yes.
Actually, I could not understand what is the exact meaning of correlation energy, sir.
I will talk about later. I will explain it in a very simple manner. Okay. Just after a few
Yeah,
slides.
thank you, sir.
So our n electron system that is interacting previously in Hartree fog, previously before this Hornbook-Kamm theorem. So the ideal picture is the electrons are interacting with each other. You cannot neglect the interaction. Okay. So this interacting. So we have the kinetic energy of the system and we have a external potential energy of the system. There are two terms of the energy: kinetic energy and potential energy. Okay. And when we solve this, our Schrodinger equation for this to get this kinetic energy and potential energy, so we get our ground state density and our total energy. Okay. So if we modify this picture,
Hello, I think there is some internet connection issue. So let me contact. So there is some internet problem and he's reconnecting actually. So he'll be there. Yeah. Because there is some. Hello, can you hear me? Am I audible?
yes.
Okay.
Yes,
okay.
sir.
Oh yeah, he just joined. There was some internet problem. Okay. Thank you for your patience.
Sure. So can you see my slides?
Yeah, I can see your slides.
Okay. So the n electron interacting picture was approximated by Hohenberg and Kohn as non-interacting one electron system. So they did a modification, which I talked earlier, as the kinetic energy is now represented as kinetic energy of non-interacting electrons, and our potential energy was approximated as effective potential, and it contained few extra term which was taken away from the kinetic energy term as an interacting term, and it is represented. So we did nothing. Hohenberg and Kohn, they did nothing, but they break the kinetic energy part into two terms, and it clubbed the interacting part with the potential energy, and these two terms, the kinetic E kinetic plus U, and also the E kinetic non-interactive plus U effective, will give us the total energy as same. So they did a modification so that they can solve the many body equation in a simpler manner. And that's why we get a exchange correlation term while solving the non-interacting one-electron system. Okay, so talking about the electrons, the exchange and correlation energy or exchange and correlation terms. So we remember the Pauli exclusion principle that no two electrons can have the same, they cannot occupy the same states. Okay, so in order to satisfy that thing, what Dirac did, Heisenberg and Dirac did, they came up with the antisymmetric nature of the electron. They gave antisymmetric wave functions. So if you replace the position of one electron with the other, we will have an exchange term that we have seen earlier. So, and the two electrons, even if they have a different spin, so they can stay at same site, but eventually they will have the same charge. The charge is not going to be different. So no two electrons can stay at the same position having different spins because they have the same charges. So because the same charges also they repel each other or they interact because of the charges, and they give us a term of energy term of correlation. So two electrons, they are at same position, so they will repel each other. So in order to combine these two electrons in a system, there is a hypothetical concept of exchange hole. So there will be a hole in between two electrons that will bind the two electrons together in a system. And also the two electrons, though having this different spin, but they have the same charge, they will repel each other. So in order to bind the two electrons in a system, there is a hypothetical correlation hole. So this correlation hole will interact with the two electrons and it will bind the system. So this, because of the interaction of the spins, we are having the exchange energy terms, and interaction of the same charges electrons, we have the correlation term. So I think it is now clear. You have a little bit idea of about the correlation energy. Someone was asking the question.
Yes, sir.
Okay.
Yes, sir.
So one term is because of the same spin, and one term is because of the, though having a different spin, but the same charges will be always will be there. So you cannot neglect that, and they will have a kind of a repulsion. So that will continue to a correlation term. So this is a quantum mechanical term in this picture, which was not present in either of the Hartree or Hartree-Fock term, and also on the Thomas Fermi term, in Thomas Fermi theorem or approach. So this, we had this term exchange correlation term. So we have non-interacting kinetic energy that is easier to solve in a system, and we have effective potential. The effective potential contains the Hartree term, which contains the electron nucleus interaction energy term, and it contains the exchange correlation term. One is for exchange energy and another is for correlation energy. And in order to approximate this exchange correlation in the system, there are different functionals given for that, as we study as exchange correlation functionals. So there is one approximation to estimate this exchange correlation functional is local density approximation, where we treat the electron density locally and we assume that this electron density is constant all over the system. So if we understand this local density approximation in a pictorial manner, so we have a picture of Mona Lisa here on the left hand side. It's a black and white picture. So we can see the shades in the picture. So we can have a darker shade, lighter shade, and all kind of complexion. So suppose if we want to reproduce this picture with local density approximation, so what we did it, we considered the electron densities are constant all over the system. So we chose a part of the density of this Mona Lisa picture, suppose this kind of electron density, and then we try to reproduce this picture. So what we will get is, we will get this kind of picture, which will be very much different from the real picture, and we will not get a clear idea about the system, and that will lead to a wrong property prediction. Okay, so if you talk about a little mathematical term, so this exchange correlation term in local density approximation, the exchange term is of the power of 1/3 of density, see the constant term, and the correlation term is a log term of r plus, that is Wigner's radius. So you know Wigner's radius, it is, you can assume in broadly speaking that it will be you kind of a cell in a reciprocal lattice, and what is the separation from a lattice site. So these two terms are represented in this fashion in local density approximation. So local density approximation, they have given us fairly good result in terms of metallic systems, because in metals the electron density is nearly same all over the place, because electrons are freely flowing in the material. So it is almost everywhere, every time. So for metal, it gives a good properties which are experimentally similar. And but this LDA, it overestimates the exchange energy and it's underestimate the correlation energy. So this, what this means? This means that the exchange energy computed by using the local density approximation will be higher than the actual exchange energy. And the correlation energy computed by this using the local density approximation for exchange correlation will be underestimated, will be lesser than the actual correlation energy. And these two terms taken together will compensate each other and we get a fairly good picture. Okay, but if we go on to solve this solve this Schrodinger equation using Hornberg-Kohn theorem and taking the exchange correlation term in terms of local density approximation. So what will be the shortcomings, or what will be the how the properties will be? That lattice parameter will be underestimated for any material. Okay, and the absorption energy of any atom on any surface will be overestimated. It will be higher than the actual. And if you are doing diffusion modeling or the diffusion experiment by DFT using LDA approximation, so you will get the diffusion barrier as underestimated. The spins and the orbital moments of the electrons will also be underestimated for any atom if you use LDA approximation. The band gaps of any semiconducting or insulating material will be underestimated. If the system is strongly correlated, where you have d orbital electrons contributing as a valence electron in the system, that you cannot describe correctly with LDA. The result will be totally wrong. And also the weak bonds like van der Waals bonds, etc., will not be explained with LDA approximation. So there were shortcomings of LDA approximation. So people improved that LDA approximation, and they came up with generalized gradient approximation, that is GGA. So if we understand this GGA is, if you see the expression for the GGA, so GGA has this exchange correlation term which is coming from LDA, dependent on density. And also we have a FS term, this is a factor term, and this factor term is composed of electron density rho of the power of 4/3, and also there is a term for the gradient of density. So if you want to imagine that this GGA functional or the GGA expression for the estimation of exchange and correlation energy in the many body interacting system is composed of what is the local density around that electron or around that nuclei, where we have considered as one single electron, and how the density is changing with respect to the space. Okay, so in many body system, we solve one electron system at a time, n number of times. So what is the density of electrons or the electronic density at around that particular electron, and how the electronic density is changing with the separation from that electron. So this LGA term, which contains the density as well as the gradient of density in all of the material, and this is what it was missing in LDA. So LDA, here this actual picture is we have a density here at a higher density and lower density at some place in the picture. So if you consider only single considering the density as constant, So we will get a wrong picture. If you consider the density gradient also, how the density is changing in the material, so that will give us the real and correct picture. Okay, so what are the trends of GGA is? So GGA gives every property, it predicts every properties with around 1 to 3% of error, which is fairly good enough. And it also produces lattice constant, slightly increase in lattice constant, because there are other interactions which is not considered in GGA. Okay, and if you calculate the cohesion energy, you will get a little bit smaller cohesion energy than the actual experimental cohesion energy. And if you want to calculate the bond length with using the GGA functional in DFT, you will get a slightly higher bond length. So these are what GGA will give. So if you want to predict material property, it will be within error of, so this lattice parameter or cohesion energy or bond length will not be higher than 1 to 5% of error. Okay. And the limitations for GGA is that you cannot apply this GGA for strongly localized orbitals, say for D and F electron orbitals. And but the major drawback for GGA is the band gap in any semiconducting or insulating material will be underestimated by up to 50%. For example, if I say with GGA calculation, the band gap for silicon will be around 0.7 electron volt. And the experimental band gap is around, anybody? Can anybody say what is the experimental band gap of silicon?
1.1 electron volts.
1.1 electron volt. So the experimental band gap is 1.1 electron volt, and the DF band gap. So LDA will fail for the band gap, we know, because it's not good for semiconducting a metallic insulating system. But even if you apply the improved version, the improved formalism of exchange correlation functional, you will get a band gap of around 0.7 electron volt. So GGA will not give you a correct band gap. Okay, but rest of the property will be fine with the experimental data. Okay. So the approach to solve this Kohn-Sham equation is by self-consistent method. Okay. So how we do is, so we take our system, okay, any material, say we have our bulk iron or copper or nickel or any material. So we identify the position of the atoms, where they are, what are their coordinates, and we construct our unit cell or lead, our material, okay, unit cell or supercell, whatever you take, want to do calculation, and we know our lattice constant, what are the lattice constant of that particular unit cell. Okay, with that, and with Hartree and Hartree-Fock approach, people have computed the potential energy for each atoms. Okay, so potential energy for each atoms are used in the calculation in the beginning, and with that we solve the Schrodinger equation with that potential potential atom, and we know the wave function of each atom. Okay, so with that wave function we construct our guess wave function, and we try to solve the Schrodinger equation, our density or Hornberg-Kohn equation, and we get our density. Okay, with density we compute the effective potential energy, because our potential energy is a function of density, as I've shown earlier. And then with that potential energy, we put it into the Hornberg-Kohn theorem, or with the Hornberg-Kohn theorem, we solve this Hornberg-Kohn equation with that density, and we get our total energy. Okay, and then with the total energy, we again put it into our Hamiltonian, and we try to get our density, charge density. And if the charge density, which now we have computed, is different from the guess charge density, which is computed from the atomic charge densities, if they are different, then again it is solved for one cycle, and then we compare the charge density of output and input charge densities, and we solve that Hornberg-Kohn equations for n number of times till we get a convergence of the charge density where our input and output charge densities are almost constant. And we give a tolerance or our convergence criteria in terms of energy, that if our energy, suppose the output and input energy computed from the different densities, input and output charge densities, are of the order of 10 to the minus 5 electron volt or minus 4 electron volt or minus 3 electron volt, then we assume that our calculation has converged. And then we, from that energy, we compute our total lattice constant or pressure in the unit cell or bulk modulus or forces, what are the forces on the atoms, by using these equations. So solving quantum equation is nothing but doing self-consistent iteration of the Hamiltonian, that many body system, taking that density, gas density, charge density, which is taken from the overlap of all atomic charge densities, and we do it iteratively till we get our results converged. Okay, so the basic difference from function, wave function method and density function method is, for n electron system, our wave function will become 3n dimensional, because for each electrons we will have 3 coordinates for our position, x1, y1, r, z1, that is r. So for our electron system, it will be 3n dimensional problem. Okay, and that there is correlation energy is not included in Hartree or Hartree-Fock method. Okay, so in density functional method, our n electron system will now be represented as n number of systems having only 1 electrons. So now we have to solve only 1 electron system, but n number of times, and each system will have only 3 dimensions, because each electron will only have 3 coordinates, x, y, and z. So it is relatively simpler in terms of solving each equation, but we will have to solve n number of times. And the correlation interaction is taken care in this density functional method. So we get a fairly good result in comparison to the Hartree-Fock method. Okay. So in order to solve this any many body system with DFT, so we have 2 kind of approaches. One is we consider all electrons of the atoms as our valence electron. That means all electrons will contribute to the deciding the property of the material. Or we can have a pseudo potential where our electrons will be split into 2 different parts. One is the valence part of the electrons and the core part of the electrons. The core electrons will be nearer to the nucleus, and the valence electron will be far away from the nucleus. And these valence electrons are what we have studied previously in our previous classes of our undergraduates, that these valence electrons will be the one which decides the property of the material. Okay. And in all electrons, we have different methods of solving our quantum equation by LAPW, that is linearly augmented plane wave method, or we make a muffin tin orbitals and we do the calculations. And in pseudo potential method, we have an effective potential, that is approximated potential of the real potential of the atoms, and we use plane wave basis set for our wave function. Our wave function will be in the form of plane wave, that is a constant terms times exponential to the I k dot r. Okay, so there are few different codes based on all electron methods and pseudo potential methods which are available, that is Abinit, Castep, ELK, quantum espresso, Siesta, VASP, Min2K. So these codes are based on different approaches how we solve. Either you consider all the electrons as a property making electrons and we do the computation, or you take only the valence electron as our electrons which decides the property of the material, and you use the approximated pseudo potential for that electronic distribution, and you use plane wave and you do the calculations. So all electrons, if you use all electron method of solving DFT, so that will be very much time consuming because the number of electrons in the system will be very huge. And if you use this pseudo potential based method, so the number of electrons in the system will be very less because it is only composed of the valence electrons. Okay, so how we understand this is, so this is for carbon. So we have a nucleus of +6 charge, and we have two orbitals of -2 charge, that is 1s, and we have our 1s and 2p -4. So this is the real picture. So if you do consider the pseudo potential, yes, someone is saying something. So when you consider pseudo potential, so what we do is the core electrons are considered into the nucleus. So our nucleus charge will be reduced now from 6 to 4, because this -2 electrons is now considered as a nucleus. So our nuclear potential will be approximated, okay, and our total electrons remaining in the atom will be -4. So now we have reduced the nuclear potential, and also we have reduced the number of electrons in the system. So in this way, our computation will become less expensive. Okay, so if you see the wave function and the potential of our all electrons and pseudo electrons, so if you see here, you can see my cursor. So there is a ripple in the wave function of the all electrons, because it's near to the core, and there is more number of oscillations. And if you see this for the pseudo electron, it is smoothly increasing up to a cutoff radius, and then it smoothly decay. So there is a smooth wave function, so it will be easier to solve, because we will have no nodes in the wave function, and it will be less computationally expensive. And also the pseudo potential, if you see the external potential, how it is. So since this is the all electron potential, so if you see, it is it's sharply like increasing, and if you see the external potential energy for our pseudo potential, so it decays smoothly, and then it after a cutoff radius, if you see this potential of the nucleus, it matches well with the all electron potential, and also the wave function after a cutoff radius matches well with the wave function of the all electron wave function. So if we consider our calculation in pseudo potential way, if you take our pseudo potential for our calculation of solving our constant equation, so after a cutoff radius, we will have our the wave function as well as the potential identical to the all electrons. So there will be no difference in the property of the atoms if we do the calculation with pseudo potential or with the all electron. The only thing is the all electron computation will be a lot heavier, and the pseudo potential method will give us a relatively easier way to solve. So how we make a pseudo potential any atom is, we select an atom, okay, and we calculate the all electron potential for that atom. That is done by Hartree-Fock method. You can compute the all electron potential, and you can calculate the wave function, and then we decide a cutoff radius RC. Okay, so beyond that RC, we take all those electrons as a core electron, and we combine it with the nucleus, and beyond that RC, our wave function is identical to the all electron wave function, and our potential is identical to the all electron wave potential, and solving our quantum equation for that that part of wave function or that part of potential beyond RC will give us the same result. So basically, for an atom, we decide a radius, and then we combine the electrons with the nucleus, and we do the computation for Hartree-Fock, and we get the potential and wave function. Okay, so what are the benefits? As I talked, that it will be we can write our pseudo potential wave function as a plane wave, and plane wave are very simplest form of wave function. Okay, and it will be less expensive in computation, and the errors are also less, because in all electron methods you have the core electrons contributing to the properties, and the core electrons, the potential the wave function is oscillating, and if we do not approximate that in our solving the quantum equation, so that will give us error, and also the relativistic effect will be easier, because what we are doing is, because our core electrons are nearest to the nucleus, so they will have a stronger interaction, and the relativistic effect will be heavier on the core electrons. So if you eliminate those core electrons from our computation, so the remaining are the valence electrons, and that will be easier to solve in relativistic approach. Okay, so how we do our computation for a real solid in DFT codes is like we have our crystal, okay, as you can see, and in crystal we have our lattice points, so we can take our lattice as we want. It can be cubic or rectangular or hexagonal, whatever. And in the reciprocal space, we will have a k space, or we'll have k points for our lattice. And if you see in the k point, there will be some symmetry, because every crystal has some kind of symmetry, and we can reduce our whole of the k space in irreducible Brillouin zone, which will be few fraction of our complete k space, and we will do our computation only in the irreducible Brillouin zone, that is this part. And for the total our crystal, this part will give the identical result even we solve for whole of the reciprocal space. Only thing is, if you solve for the whole of the reciprocal space, it will take more time, and if you solve for this irreducible Brillouin zone, it will take less time, but it will give us, because there is symmetry in whole of the k space. Okay, so k point, how we do the k point sampling, we generally use few methods like Monk-Pack method. So if you use this method, so it will generate evenly spaced k points in whole of the irreducible Brillouin zone. So it will be the k points in the Brillouin zone will be evenly spaced, and it will be symmetrical. Okay, and also the thing is that if you have a reciprocal space and you have a k points in those reciprocal space, and if we have our lattices, our reciprocal lattices as B1 and B2, and in the center of our lattice, that is the point where B1, B2 meets, is in the center of the cell, but it is not on any of the k points. So this will give us even unevenly spaced k points within our reciprocal lattice vectors B and B. Even if we do a symmetric generation of k points, and our center of the reciprocal lattice vector are not on any k points, then also if you see along this dotted line, above and below this dotted line along B1 and B2, we do not have evenly spaced k points. Okay, so if we shift our reciprocal lattice vectors on a k point, and that k point is on the center of the cell, so this will give us evenly spaced k points, and also the k points will be equal along B1 and B2 reciprocal lattice, and this is called as shifted to gamma, or gamma centered our irreducible Brillouin zone. So it is really easier to do the computation in gamma shifted Brillouin zone, where our center of the our origin of the lattice meets at k point. Okay, so these all things I think you have these were given in previous talks also, but I will say a little bit about that. So one thing is block theorem, that we have our plane wave that is represented by E exponential I k dot x or k dot r. Okay, so this is not periodic. So if each block is our Brillouin zone, so it's not periodic in each of the Brillouin zone. But if we mix this our plane wave with the periodic function, that u k x function of x, so then our wave function becomes this psi k, and if you see this psi k is now periodic in each of the Brillouin zones. So from here to here, this is periodic. So from this point to this point, if you see, it's all same. So now if our wave function is similar in all of the Brillouin zone, so if you do the computation only in one Brillouin zone, this will give the same result as if you solve for all of the Brillouin zone or in any of the Brillouin zone. That's why we use the symmetry of the crystal in the reciprocal space, and we reduce our computational time and computational cost. Okay. So, wait a minute. Okay. So now we have our periodic wave function in our reciprocal space, in our case space, in our Billion zone. And if G is our reciprocal wave vector, so if we change our K or reciprocal by periodic wave vector in the K space, K plus G, so we will have the same wave function, and our energy will also be the same if we do our computation for 1 billion zone, or for 2 billion zone, or for 3 billion zone as we move in our K space. Okay, so there is one criteria which we get from our reciprocal, that is space, is that the kinetic energy will be equal to half of K plus G whole square, okay, mod of square of K plus G. So K is our lattice wave vector, and G is the periodic wave vector of in reciprocal lattice, and the cutoff energy for our wave function, that is, this gives us a cutoff energy part, exponential ik dot r. So this cutoff energy for our calculation for the particular wave function should be greater than or equal to half of K plus G whole square. So with the use of periodicity, we are going to reduce our computational time and cost, and also with the periodicity we can define how much large our wave function should be, or what should be the cutoff energy for our wave function, because the crystal is periodic and it extends up to infinity. So at some point somewhere we have to take a cutoff for our wave function and for our wave energy, and that is decided by this criteria, half of kg mod square. Okay, so as you see in insulator and semiconductors, the density of the electrons, it decays to zero smoothly. Okay, in our case space. But for metals, if you see for metals at 0 Kelvin, you have electrons filled in all the orbitals, but at 0 Kelvin at the Fermi level, there is suddenly the electron density decreased to zero. Okay, so for insulator and semiconductor material, solving the quantum equation is relatively easy, because we have a smooth decrease in the charge density, so there will be smooth decrease in the wave function also. But for metals, that is not that easy, because the charge density or the wave function decays abruptly at Fermi level. So there are different methods to tune this metal property with the help of smearing. And the smearing is nothing but we add a finite or a fictional electronic temperature term. Like in Gaussian smearing, we add of the order of 0.1 electron volt of energy to our wave function, okay, to our orbitals, so that it can act as a energy can have an equivalence in temperature. So that energy will have equivalence in temperature, and it will with temperature, we know that the electron population in any state can be changed slightly. So with that increment of smearing of around 0.1 electron volt, the occupation or the distribution of the electrons in any orbital is changed in a Gaussian type form, and then we do our computation. So it broadens the state of energy at the Fermi level for the metal, and then we will have decreasing in energy very smoothly, but not abruptly. And also in Fermi smearing, so see if you can see this distribution of electrons with energy. So here it is filled. So ideally at 0 K, if you do not have smearing, so the density will from here it will change to zero. It will go to zero. Okay. So there will be a soft discontinuity, and it will cause error in our calculation. But if you do the smearing, either Gaussian or smearing or Fermi smearing, so what will be the electron density, instead of going down at EF, it will start decreasing much below before EF, and it will smoothly decrease and it will cross the Fermi level, and then it will come to zero at some point higher than the Fermi energy. So our computation is up to Fermi energy because all the electrons are up to Fermi level, and the property will be decided by the electrons which are filled. So we do our computation with a small kind of smearing, either in the shape of Fermi drag distribution, this, or we, sorry, or we make a Gaussian kind of distribution around Fermi in Fermi drag distribution, and we do our computation for metallic system, so that we just neglect the we can just escape from the discontinuity, and we have a smooth variation of electronic occupation or electronic density at the Fermi level, and we do the computation, and that result does not vary much from the actual results. Okay. So smearings are used for metallic system to make our computational process easier. Okay, and also there is Maxwell-Paxton smearing. In this smearing, we introduce a parameter sigma, that is our smearing parameter, and we tune this sigma, and this sigma adds a slightly a Gaussian function into our electronic occupation, and is similar to our Gaussian smearing. And there is tetrahedron smearing, in which whole of our irreducible beryllium zone IBZ is broken into several number of tetrahedrons. Okay, so by breaking in several tetrahedrons, we will have small spaces, and we do our computation for those small tetrahedrons, and we interpolate our energies for whole of the system, and by this also we can escape our this abrupt occupancy going to zero in our electron distribution. Okay, so whatever till now we have just talked, like for Hartree or Hartree-Fock, or even for Cornsham approach of DFT, that was for single electron. Okay, and that too for electron having no spin. We only talk about that electrons, the formalism is for electrons having no spin. I mean, like only having a particular kind of spin, either up or down. So that approach can be extended for spin polarized DFT. That is, we will now consider two kind of spin, that is spin up and spin down electrons in our calculation, and nothing will change but our wave function in Hartree-Fock approach, which has a position for our one spin, that is for either for up, then we will have another coordinates for our down spin. And in terms of density functional theory, where we had n of r, that is density of r, so that is for one spin, so we will have another part in the density that is for another spin channel, that is one for spin up and spin down. Also, we can have DFT for fractional occupancies, just like we do smearing for our solving this metallic system. Similarly, we apply this DFT, or we can just tune the formalism of DFT, and we can do for fractional occupancies also, where the states are not totally filled. And also this DFT is for ground state system, where we have one electron, we consider one electron at a time in our many body system, and we do the computation, but that one electron is in its ground state. Okay, so if that electron is in higher state, or it is excited, so we will have a different formalism for our excited state DFT. And also this density functional theory calculation, or the Hartree-Fock approach calculations, they are done for 0 Kelvin thing. They are ground state, and ground state is at 0 Kelvin temperature. So also, if you want to study our system at some finite temperature, then we will have a finite temperature DFT. So in our system, in our Hamiltonian, we will have a temperature term also, energy arising from temperature term. And also, if you want to study our system with time, how the system is evolving with time, how the property is changing with time, then we will have time dependent DFT. And then we have linear scaling DFT. That is like if you want to the order. So the order of the computation in DFT is of the order of n to the power 3, because we have n electrons and we have 3 degrees of coordinates, 3 degrees of freedom or 3 coordinates for each electron. So we have order of n to the power 3. But suppose we have this n is too huge, then this n to the power 3 will be also very large. We have like thousands of atoms. So in that case, we apply a different approach of DFT, that is linear scaling. In that, our order will be linear, that is n to the power 1. So this is a little bit different from that. So these are different flavors of DFT. Like we can modify our DFT approach on the CONSHAM, and we can do different kind of studies. And where this DFT can be used in its like ground state DFT or spin polarized DFT for our structural relaxation, where we want to change, like we have some material and we don't know the lattice parameter, then we can relax the structure and we can get a correct lattice parameter. Or we can do the phase stability, like suppose we some particular material, they exist in few different phases, like it is in cubic phase, orthorhombic phase, or hexagonal phase, or whatever. So also then we can apply this DFT and we can predict the stability of which any particular phase or which phase is stable for that particular material. And we can also calculate the phonon dispersion, how the phonons band structure is, or what is the stability of mechanical stability of the material, it is either stable or not. And we can also predict the property that if any material can be either metallic, or it can be insulator, or it can be semiconductor, or what can be the band gap of that insulating semiconducting material. All these things we can obviously we can calculate the band structure. But there are few limitations to this DFT, that as I also discussed in GGA part, that it will not give the correct band gap with GGA. And if you want to observe the optical properties or excitonic effects, that is, we have to do DFT for excited state, or we have to do we have to use other method which is different from DFT. And also this LDA fails poorly, but the GGA also does not give a good result for strongly correlated system where we have interacting electrons of d and f orbitals. So these are few limitations of density functional theory. But if you talk about this structural relaxation, phase stability, phonon, property prediction, band structure, you will get fairly good with DFT using the GGA approximation. There are few things which we can add with GGA and we get a correct band gap also. Just like I said, the example of silicon, that GGA gives 0.7 electron volt of band gap and the experimental band gap is 1.1. But with GGA applying something extra terms, we can get a band gap of around 1 also. So all these lectures which I have given, this is taken from book Jun Gun Lee, Computational Material Science. So you can consult this book. It's a good book for learning the basic of DFT. And also there are basic other books like ABC of DFT. You can also you can refer that book. So this is for this session. If there are questions and doubts, then we can discuss that. Thanks. So any questions? Hello. Rick?
Yeah.
So yeah.
Thank you for a nice presentation. Yeah. So any questions from the participants? So you can ask questions. So I hope in the second session you are going to discuss more about the applications, right?
Yeah, I will talk about this few application which I mentioned in the last part, that the phase stability or property predictions, all those things.
Yeah.
But yeah, we cannot go into how we do that. I will give the approach for that. I will talk about the approach, but we cannot show that how it is done. Because that is because we have to construct all of the things and we have to do the computation and show. But yeah, I will explain how it is done. So if anybody who is doing DFT or learning DFT, so or if we do some small calculations of DFT, so he can try those kind of calculations. They can try those kind of calculations. So they will get the approach for that.